Hello, here's another video on blockchain basics. We've talked before about the problem blockchain solves, and then we talked about cryptography. But I think now it's time to give a definition of the term blockchain and explain a little bit the data structure that it uses. So here's my definition. A blockchain is a distributed ledger implemented using a cryptographically linked list data structure. So the important terms here are distributed ledger, and we'll define that in more detail in a minute. But there are different types of distributed ledgers, and a blockchain uses a linked list data structure to maintain this ledger. The term is often used in a wider sense for all types of distributed ledgers, but really a blockchain, where the term comes from, is a chain of blocks, which is a linked list data structure. The other important work here is cryptographically linked. So there's a cryptographic linkage between the elements in the data structure that provide certain properties, which we'll also discuss in this video. So if we talk about a distributed ledger, we really have to find distributed ledger as well. And for me, a distributed ledger is a replicated database of transactions, which is maintained consistently over a peer-to-peer network. So the data structure is replicated on each node on a network on which there's no coordinator, there's no one defining the correct version of this database. So they have to reach consensus on a correct version. And all nodes are equal in the system. And the other important word here is consistently, right? So this ledger has to be maintained consistently, and this really means we need exactly the same version and order of the transactions in this ledger on each of the nodes. So every copy is exactly the same. And we could add here something about Byzantine fault tolerance, but really what we mean by this is that this consistency should be maintained even if there are some actors in the system that try to cheat the system. So there might be malicious nodes that try to manipulate the ledger. And the system should maintain consistency even in that scenario. So the ledger itself is an information repository which has to have certain properties. So first of all, it has to be distributed, fully replicated. But then anything in that information repository, which is really a list of transactions, has to be transparent. Every party in the system should be able to see everything of a transaction. The system has to be trustless. Trustless in the sense that we don't have to trust a central entity or some coordinator or anything like that. Instead, we trust a mathematical protocol, a cryptographic protocol. That's related to consensus. So there's a consensus on what is the correct version of the repository. And importantly, all the information in there must be immutable. And this really means that it should not be no one should be able to manipulate this and change or remove transactions. And this is a very important property that allows many of these blockchain applications to do what they're supposed to do. Obviously, with immutability, what we really mean is that any attempt at changing a transaction should be easily detectable by anyone. So then we have the actual data structure itself, which is a chain of blocks, which is where the term blockchain comes from. So starting from a first block, which usually called the Genesis block, we just fill this up as transactions. Every so often a new block is created and transactions are confirmed by adding them into this block. In Bitcoin, that's done by the miners. We will talk in a separate video about different ways of doing this and how it's done exactly in different systems. But let's assume Bitcoin for a moment. So miners select transactions from a list of unconfirmed transactions, and they're confirmed by being included in a block. Now, this block is added to the end of the chain of blocks, and it references the earlier block, and by that we generate this long list of blocks. It's basically a linked list data structure. So though the actual link between the block is done cryptographically, and what that means is that here, if we look at the structure of a block, though there's a timestamp, there's a nonce which is used in the mining process, which we'll discuss afterwards, and there are transactions. Actually, there's a transaction root, which is usually the root of some hash tree, which really means the transactions don't live within the block, but they're just referenced. This is called the Merkle tree. I might explain this in another video in more detail. In Ethereum, it's called the Merkle-Patrizia tree, but basically it's a cryptographic data structure that makes finding these transactions or making sure that they're not changed and storing them a bit more efficient. But anyway, the block itself has this very important field, which is the hash of the previous block. So in this example here, block 11 has the link to block 10 by including the hash of the block header. And that way we can guarantee this immutability property in a way, because if someone wanted to change something on the blockchain, these hashes wouldn't be correct anymore. So if I change block 10, then the hash in block 11 is not correct anymore. So there's a cryptographic linkage between all these blocks that would be broken, and that's obviously very important. So the next step is that we have to maintain this ledger in sync, and that's really what we often talk about as Bitcoin mining, or as proof of work, or proof of stake, consensus. But basically there's two very important steps in this. Now, first we have to choose fairly a block producer to produce the next block. Someone has to be elected in a way to provide the next block. Otherwise there'll be a lot of nodes trying to produce different blocks at the same time. And then once we have this block, the whole system needs to reach a consensus of whether this block is correct and should be included in the blockchain or not. And all this is called consensus, and we'll discuss this in the next video in a lot of detail.